My name is Nick Linthorne, and I'm going to be talking about using counter-movement jump variables to monitor the recovery from match fatigue in football players. I'd like to acknowledge my co-authors, Antonio Gregorio and Hussein Thapa, who are students at Brunel University, London. So in a football match, the player performs many high-intensity eccentric muscle actions whenever they're doing things like sprinting, jumping, and cutting. And these actions can induce substantial delayed neuromuscular fatigue in the player. This is believed to be due to micro-trauma to the muscle fibers in the player. So the player recovers after the match over the following 1 to 3 days. And in football, you usually play a match every 5 to 7 days. So what the coach or the trainer wants to do is monitor the players to see if they've recovered from the fatigue and are ready to return to training. The most common method of monitoring the fatigue status of a player is with a counter-movement jump test. So many professional teams have force platforms and they perform daily testing of their players. The force platform software generates many jump variables, and you usually calculate the average of 3 to 6 jump trials. However, it's not clear whether jump variables are suitable for monitoring the recovery in the individual player. There have been many studies, group studies, that show recovery from fatigue in players. However, it's not clear that you can also see the recovery from fatigue in the individual player. Also, jump height might not be the most sensitive jump variable. It is suspected that some jump variables might be more sensitive than jump height for monitoring recovery from fatigue. So the aims of this study were to work out whether you can use counter-movement jump variables to monitor the time course of recovery from match fatigue in the individual player, and also to identify the jump variables that are best for monitoring the fatigue status of the player. So we had two hypotheses. The first was that jump variables are reliable and that a match induces a substantial change in these jump variables, and therefore you can detect the time course of recovery in the individual player. The second hypothesis was that some jump variables show a longer recovery than jump height. So this is an experimental study, and it was characterized by intensive testing and a detailed analysis of the individual player. The participant in this study was a skilled female football player, and there were 3 key stages in the study. So we first did some baseline testing where we got the player to perform 60 jumps over 4 days. So there were 3 testing sessions per day. Then we got the player to play in a football match. And this would induce some delayed fatigue in the player. And then we did some recovery testing. So straight after the match, we got the player to do 100 jumps over 5 days with 3 test sessions per day. We actually had 2 studies. So after the first match, we waited a few weeks and then got the player to play a match again. And this time we got the player to do 100 jumps over a much shorter time span. This time it was 2 days with 8 testing sessions per day. So we got the player to do the jumps on a force platform, and the jumps were analysed with BioWare software. And we divided up the jump variables into performance variables. So these were things like the jump height, calculated using the impulse momentum method, the jump height calculated using the flight time method, and the peak upward speed. And we had some other variables that characterize the jumper's technique. So this is the counter movement depth, the maximum downward speed, the force at the bottom of the counter movement, the maximum upward force, and the takeoff height. So what we wanted to do was to monitor the recovery in the jump data. So we fitted an exponential curve to the jump data, and we were trying to get a value for the time constant of this exponential recovery to baseline. In case the data didn't quite follow an exponential fit, we also had a low S fit to the data, so this would show the general trend in the data. As well as jump variables, we also got the player to answer a well-being questionnaire where they had questions about their fatigue, sleep, and muscle soreness, and this was done every day. So here are some results. So these are results from the baseline testing. So this is the the player's jump height over the 4 days of baseline testing, and we can see that the jump data is consistent over the four days, and there's no evidence of a longitudinal trend or any diurnal variation. So this dashed line is the general trend in the data, and the solid lines, well, that's the lowest fit, and that's showing that there wasn't any pattern. These are just random fluctuations in the data. So a few days after the baseline, we got the player to play in a match. And so on this plot here, so here's the match, and here's the jump straight after the match. So there was some evidence of change due to the match, but it wasn't very substantial. And in the 5 days after the match, there was no clear evidence of an exponential recovery to baseline. So most of the jump variables looked like this. And this is the second study. So a few weeks later, played in another match, jump testing straight after the match. And in the 2 days following, again, we didn't see any clear evidence of an exponential recovery to baseline. So when we did fit an exponential curve, we got a time constant, but there's a very large confidence interval in these time constants, and so they weren't reliable. So here's some more of the data. So these are some of the different variables. So this is the baseline testing showing consistent patterns in the jump variables. And this is in the playing the first match and looking at the recovery over the following 5 days, showing no exponential trend in the data. And this is a few weeks later, play another match. And again, there's no obvious exponential recovery in the jump data. Down the bottom here, this is the well-being scores, and these are a little bit more interesting. This is the baseline data for the well-being score, so we can see it's consistent over the 5 days of baseline 4 days of baseline testing. And this is when you play a match, and straight after the match, there's a decrease in the well-being score and a gradual trend towards recovery over the following 4 or 5 days. And this is the second match, and again we're saying the same thing, but a slightly more rapid recovery. So this is what we actually expected, because this match was right at the very beginning of the season. So this player didn't do much pre-season training, so they were expecting their first match to be quite stressful, and that's what showed up in the well-being questionnaire data. And this match was played several weeks later when the player probably was a little bit fitter, probably had a slightly more rapid recovery. So the main findings were that the results don't support our hypotheses. So although the jump variables were reliable, the matches didn't induce large changes in the jump variables. And we couldn't detect a time course of recovery. So when we had an exponential fit, we weren't able to get reliable time constants out. And because we didn't get reliable time constants, we couldn't discriminate between the variables. We couldn't say that one variable was more sensitive than another jump variable. What we did find was the well-being questionnaire might be better than jump variables for monitoring recovery from a match. So our data suggests that the match did produce muscle damage and delayed fatigue, but this was not evident in the jump data. So in conclusion, for the player in this study, the time course of recovery in the days after a match was too small to detect using the selected jump variables. Thank you for watching this presentation, and we hope that you find it useful.